Hello there. This is a video for ENME 303 Numerical Methods. This is for the UMBC Fall 2013 semester project. The topic of this video will be LaGrange Interpolating Polynomials and how they're constructed. LaGrange Interpolating Polynomials are commonly used to interpolate between two given points by fitting a curve between them. The complexity of this curve depends on its order, which also determines which points it passes through. As you can see below, a first order curve, which would end up being a line, would only pass through 2 points, a second order would pass through 3 points, and a third order would pass through 4 points, and so on. Note that these are not the exact curves given points of this nature, but just conceptual drawings for you to understand what's going on. So in order to create these curves, a whole set of equations need to be used. The first being the basic Lagrange interpolating polynomial equation, which states that your polynomial will equal the summation of your Lagrange terms times your function terms. And your Lagrange terms will equal this monster over here. As you can see, some words that might come to mind when you see how these equations are created would be alphabet soup, confusing, disorienting, terrifying, and so on. So when you use these terms, you end up creating general equations for first order, second order, and so on polynomials. These polynomials generally increase in complexity and usually all follow this format. So in order to construct these, a much simpler approach can be taken other than deciphering these formulas. First, the order must be chosen, and after that, order plus 1 surrounding points must be chosen. So if you are a second order interpolating polynomial, you would choose the 3 closest points to the value that you're interpolating for. After that, a framework can be laid for the overall interpolating polynomial, stating that the function that you're creating will be equal to order plus 1 points up to your last y value. Excuse me. After that, each Lagrange polynomial value, L1, L2, on to Ln, can be constructed separately. Then it needs to be put all together, and if your question prompts you to, you can plug in the value and interpolate. So I have here some example points. These points don't represent any data in particular, but they'll serve for the purposes of creating an example. Such a standard example would commonly ask that given these points, approximate the value of the function at 3.8 using second and third order Lagrange interpolating polynomials. So our first step would be to choose order plus 1 surrounding points. As you can see, the closest 3 points to 3.8 would be x equals 3, 4, and 5. So choosing those 3 points, we can then lay a framework for the polynomial overall. We can say that the polynomial f of x will equal 3 terms, given that the order is 2, each multiplied by the subsequent y value, 7, 6, and 3. So now we can start constructing our Lagrange terms. Up here I've provided a bank of terms that would be necessary to create up to a 5th order Lagrange polynomial, but since this is a second order, we can cover the 3 later points. So for our first term, n up here would be equal to 1, and since this is our first term, we would exclude the first Lagrange part, giving our first Lagrange polynomial term as x minus x sub 2 times x minus x sub 3 over x1 minus x sub 2 times x1 minus x sub 3. As you might be able to tell, we exclude the first term partially because if you had x1 equal to x1, that would make the denominator 0, making the function undefined. So for our second term, we do the same, but instead here we cover our second value, making our second Lagrange term equal to x minus x sub 1 over x2 minus x sub 1 times x minus x sub 3 over x 2 minus x sub 3. Again, we do the same for the third term, thus finishing our second order Lagrange polynomial, making this term x minus x sub 1 times x minus x sub 2 over x3 minus x sub 1 times x3 minus x sub 2. Plugging in each of our values for x sub 1, 2, and 3, we get a final Lagrange interpolating polynomial equal to x minus 4 times x minus 5 over 3 minus 4 times 3 minus 5. We plug in the points for the remaining two terms, making the second two terms equal to x minus 3 times x minus 5 over 4 minus 3 times 4 minus 5. Multiply that by your function value. I didn't mention that the first time, but you need to remember to do that. The next term will be x minus 3 times x minus 4 over 5 minus 3 times 5 minus 4. Again, multiplied by the function value. Solving this equation at x equals 3.8 will yield that your estimated y value equals 6.36. So moving on, we can move on to start the third order approximation. So as you can see, since this is the third order, we'll choose order plus 1 surrounding points, meaning that we'll need 4 points now, bringing 2 into the mix. And after that, we can lay our framework again, saying that f of x equals some large term times the first y value 4 plus another large term times the first y value times the second y value 7 plus a third large term times the third y value of 6 plus the last large term times the y value 3. So since this is a third order, we're going to need 4 terms, so we can expand our bank up here. And since it's the first term, again, we exclude the first value. And n will equal 1 again, making our Lagrange polynomial x minus x sub 2 times x minus x sub 3 times x minus x sub 4 over x1 minus x sub 2, x1 minus x sub 3, and x1 minus x sub 4. So again, we repeat the process for the next 3 terms. For term 2, n equals 2, and we exclude the second term. So we say that the second Lagrange polynomial term will equal x minus x sub 1 times x minus x sub 3 times x minus x sub 4. And likewise with the denominator, x2 minus x sub 1 times x2 minus x sub 3 times x2 minus x sub 4. Moving on to the third term, n equals 3, and we exclude the third term, making our Lagrange term x minus x sub 1 times x minus x sub 2 times x minus x sub 4 over x3 minus x1 times x3 minus x2 times x3 minus x4. Again, skipping 3. Likewise for the fourth term, n equals 4, and we skip the fourth term, making it x minus x1 times x minus x2 times x minus x3 over x4 minus x1, x4 minus x2, and again x4 minus x3. I'm not going to plug them in for this one solely because it's so long, but once you plug in your x values for x1 through 4, x1, x2, x3, and x4, you end up with x equal 3.8 will yield an approximation of y equals to 6.424. So as the order increases, you'll notice that the interpolated value does move, probably to its true answer, but without further expansion of the polynomial terms, convergence won't really be noted. It's also prudent to note that although this does work for any given number of points, most applications tend to prefer splines over LaGrange interpolating polynomials or other methods. This concludes this video.